In this section, we'll see a problem on a fixed beam subjected to UDL and a couple. So analyze the fixed beam shown in the figure. The fixed beam is subjected to UDL of 60 kN per meter on the span ASV 4 meters, and at D it has a couple 160 kN per meter. So it has a moment 160 kN meter at a distance of 2 meters from C and 2 meters from B. So total span AB is 8 meters. Yeah, coming to solution part. Now, how to proceed? So first of all, we'll take a fixed beam subjected to UDL only. We'll remove the moment there, and due to this UDL, so what are the moments we are getting? MA1 and MB1. So already we know that when there is a UDL subjected, when there is a fixed beam subjected to UDL on the half of the span, so we have a formula that M fixed in moment MA equal to 11 WL square by 192, MB equal to 5 WL square by 192. So substituting here, we'll get MA1 equal to minus 11 WL square by 192. So that equal to minus 11 into 60 into 8 square by 192 equal to minus 220. MB1 equal to 5 WL square by 192, that is equal to 5 into 60 into 8 square by 192 is equal to 100. Therefore, now in the second case, we will consider only the moment, removing the UDL as shown in the figure. Now we know that for fixed beam subjected to eccentric couple, the formula, the fixed end moment formula is MA equal to MB by L square 2A minus B clockwise, and MB equal to MA by L square into 2B minus A clockwise. So MA2 equal to 160 into 2 divided by 8 square into 2 into 6 minus 2 equal to 50. MB2 equal to 160 into L by 6 divided by 8 square into 2 into 2 minus 6 equal to minus 30. So if you see in the previous case, MA1 equal to minus 20 because it is anti-clockwise. MB1 is clockwise, therefore 100. So MA2 we got 50, MB2 we got minus 30. But we need a total of final fixed end moments MA equal to MA1 plus MA2, that is minus 220 plus 50 equal to minus 170 kilonewton meter. This is minus, therefore anti-clockwise. MB equal to MB1 plus MB2 equal to 100 minus 30 equal to 70 kilonewton meter. This is plus, therefore clockwise. The same MA and MB we will show in the figure. So you can see in the figure there is a UDL moment, and the final end moments MA 170 anti-clockwise, MB 70 clockwise, and reactions. Now to draw the shear force diagram, we need to find the reactions. So applying the equilibrium equation sigma Fy equal to 0 and sigma moment about B equal to 0, we can find RA and RB. So RA we will get 172.5 kilonewton when we apply sigma moment about B equal to 0. So if we apply sigma moment about B equal to 0, what we have? Minus 170 because it is anti-clockwise, plus 8 RA. So RA into 8, total distance 8, it is clockwise, therefore plus, minus 60 into 4 into 4 by 2 plus 4. So plus 160 plus 70 equal to 0. From here we'll get RA 172.5, and then substituting this sigma Fy equal to 0 equation, we will get RP equal to 67.5 kilonewton. So at A, in the shear force diagram, at A the value is 172.5 and at B 67.5, and from B to C the value is constant 67.5. So to draw the shear force diagram, we need to calculate the shear force values first. So shear force values will calculate here. Shear force in the section, at any section X between DB is equal to minus RB, that is minus 67.5 kilonewton. Between CD it is minus 67.5. Between AC the equation is minus 67.5 plus 60 into X. At C, that is X equal to 0, shear force at C equal to minus 67.5 plus 60 into 0, that is minus 67.5. In the same way at X equal to 4, that is at A, the shear force at A equal to minus 67.5 plus 60 into 4, that is 172.5 kilonewton. So from these values we can draw the shear force diagram. In the same way we can calculate bending moment values. So bending moment At any section between DB is we have equation RB into x minus 70, that is 67.5 into x minus 70. At B, that is x equal to 0, bending moment at B is minus 70 kN meter. At D, that is at x equal to 2, bending moment is 65 kN meter. Bending moment at C is 40 kN per meter. Bending moment at D is minus 95 kN per meter. Bending moment at C is 40 kN per meter. Bending moment at A is minus 970 kilonewton meter. But we need another point here, the point where shear force is becoming 0. At that point the bending moment will be maximum. So to know that point, distance x where the shear force is becoming 0 or where the point bending moment is becoming maximum, we need to equate the shear force equation between AC to 0. So equating that shear force equation AC equal to 0, minus 67.5 plus 60 into x equal to 0. From there we'll get x equal to 1.125 meter. So to get the maximum bending moment at a distance of x equal to 1.125, substitute x equal to 1.125 in the bending moment equation AC, that is 67.5 into 4 plus x minus 70 minus 160 minus 60 x square by 2. Substitute x equal to 4 here, you will get maximum bending moment value 77.96 kilonewton meter. So from, as we know all the bending moment values, we can draw the bending moment diagram as shown in the bending moment diagram is as shown in the figure.